Hello everybody, it's In Code We Trust. So today we're going to solve Leetcode 133 clone graph problem. We already solved this problem using DFS approach, and today I'm going to show you how to tackle the same problem but using BFS, breadth first search. So let's jump right into the question. And by the way, if you are curious why am I doing this in Google Doc format and not the actual Leetcode, I have a separate video for that. I'm going to have it linked in the description below. But in overall, it's this setting is very close to the actual settings you're going to get during your technical interview, and it's a good idea to practice in a setting like this. And there are a couple other reasons why. So just check that video, right? So with that being said, let's jump to the question. We are given a reference of a node in a connected undirected graph, and we need to return a deep copy clone of the graph, right? So we are given, we have an image, right? We're given this yellow graph. We need to do to make the same one, but yeah, it needs to be like a deep copy of the original graph. So and we are given this definition of a node. Let's take a look at it. So it's a public class node. Yes, and we have a var property integer and a neighbors property, which is array of nodes, and we have this constructor, right? Okay, so that's very useful. And actually, sometimes like some interviews might not even give you this description, but for simplicity, let's assume we have one. But like one thing to one thing that you might have have your interviewer ask you additionally, why this node is actually a class and not a structure. It's I think it's very valid question to ask, and I'll let you think about it on your own, guys, and give me your ideas in a link in the comments section below. All right, so back to the question. We have this class, right, and we need to make a copy of it, right? So the first thing it would be, as I have this outline of steps for the problem, let's collect information about the input. At this first step would be to ask questions. Actually, ask questions about the input, about like some clarification questions about the problem given. And at this point, it is very important to not assume anything. And because you have this opportunity to ask a person, your interviewer, you need to take advantage of it and really ask if anything is not clear. So let's think what would be a valid question to ask here. Is the first one I can come up with is actually ask if the given graph is empty. Let's say we're given this reference to a node that is, let's say it's empty and it's nil. So what if the node is nil? What do we need to return? And I think in this particular case, it can be it would make sense to return nil, or in some cases, like you would need to return, I don't know, -1 or 0, something like that. But it is very important to clarify the step with your interviewer. And another like valid question to ask is, so we are given this graph, we can see obviously that value property of each node is kind of unique. Like we don't have any duplicate values in the graph. So can we assume that the value property of a node is unique for every node? Because depending on that, like if it's not, we need some other way to differentiate between nodes. But yeah, but I think in this at this particular case, it is probably going to be the case that your interviewer is going to go ahead and say that the value property is actually unique for every node. So we can just go ahead and write it down, like unique property for every node. We spelled correct. Object. All right. So I think yes, that would be enough. So after that, we have collected some information from our interviewer. We can go ahead and try to tackle this problem. So one way to, one of the line of the thoughts I have, so obviously it's a graph problem, right? There are like a couple ways to tackle the graph problem. One is being DFS and one is being breadth first search. You also sometimes have to use like Dijkstra, but that's for weighted graphs. And we don't have weights here, so it doesn't really make sense here. But once again, we have solved this problem using DFS. Let's try to do it with BFS. So idea here is the idea here is to somehow differentiate between, like as we traverse the graph, like right, so we need to make sure that we need somehow to figure out if we have created a copy for the particular node we are at, visiting right now. And as we go through its neighbors, let's say like we are in one, as we go through its neighbors, we have like neighbor 2 and neighbor 4. We need to somehow again figure out if we have created a copy of 2 actually. So if we are at 1, we need to make a copy of 1, and then as we go through its neighbors, as we go through neighbors of the regional graph, we need to make sure like, okay, we have a connection between 2 and 1. So do we need to create a copy of 2, or we already have a copy of 2 and we just need to make a connection between those two copies, right? So that can be done actually with the use of additional data structure. In this case, I think that hash set or hash map, like or in Swift we can use dictionary, will make sense because the value property is unique for every node and it's an integer, so it's a hashable data type. So yes, we can go ahead and say that first we'll use a dictionary with an integer as key and with a node as value, and for every single node, so as we traverse it, we will check in that dictionary if we have created a copy of it. If we did, we're gonna access it through dictionary. If not, we're gonna go ahead and create a copy of a node, and also make a connection. We're gonna make connections by just adding them to the array of neighbors. All right, and to traverse it, we're gonna use BFS. All right, so once we outline our approach, we can go ahead and try to estimate the time complexity and space complexity of our approach. Let's see. So for BFS and DFS questions, it's actually very important to start with very basics, like every DFS or BFS, your time complexity, TS by the way stands for time complexity, and CS stands for space complexity. For every BFS or DFS, your time complexity is going to be E plus V, and E being standing for edge, and V will stand for vertex. So once you start with this, depending on if you have like any additional information of I don't know how many if it's a matrix, you have an idea how many vertices and how many edges you like the maximum amount you're going to have. But in this case, we don't, and it is very important to understand it's E plus V and not like E times V or any other combination of possibilities. But because number of edges for each vertex might be different, so we take in all the numbers of edges, all the connections a graph has, and we need to add all the number of vertices we have, because it can be a case that like every single this is undirected graph, but in case of if you have a directed graph, you can have multiple edges going back and forth, and the number of edges can be like bigger than the number of vertices. So it does vertex, and it does affect your overall time complexity, right? Okay, with that being said, let's jump to the space complexity. CS stands for space complexity. As we've mentioned before, we're going to use this additional dictionary. So this space complexity is going to be V of big O of V. All right. So after this step, after outlining space complexity and time complexity, you can go ahead and ask your interviewer if he agrees with your overall approach and is satisfied with time complexity and space complexity of your approach. So you can go ahead and try to code the implementation of the solution, right? It is very important step, because sometimes you might not come up with an optimal solution first, and your interviewer, in that case, your interviewer is probably going to give you a hint or like ask you if let's see if you can do better. Like if he has some idea or some approach that works faster, he's going to hesitate and try to push you in the direction of before you go and waste your time trying to implement one approach, let's see if you can come up with a different approach that your interviewer is looking for, right? Okay, so once you get approval of your interviewer and he says or she says that you can go ahead and try to code the problem, you can proceed to the next step. So, so the first step is create function definition for the problem. Let's try go ahead and do that. And once you start coding, it is very important to pay attention to how you name things, right? So it is very important, and it is something your interviewer is going to pay attention to. So let's try to name this correctly, right? So we need to create a copy, right? So we can say, oh, we need to deep copy or clone, right? We can say clone graph, and we are given, let's say we are given a reference to a node. So we can say node, and it can be optional, right? As we've discussed before, it can be an empty graph, so that's why we need to return an optional node. Let me go ahead and change the font so it does look like code. Yeah, it looks much better. So all right, so let's create another function. And as we said before, we're going to do this using breadth first search approach. And for that, we need a node reference to a node again. And we're going to return the node optional too. All right, and this node needs to be optional so we can tackle the edge case, right? Let's before we forget, let's call this BFS function in our main function. I'm going to pass node, and yeah, it's going to return node, so it does match, so we are good. All right, so before, let's start with a guard, right? Covering edge cases. Let node equal node, else we're going to return nil. So that covers our edge case if the graph is empty. And now we need to traverse our graph, right? So for BFS, we need a couple things, right? We need queue to hold our nodes, right? So it's going to be an array of nodes. And by the way, I'm saying that it's going to be a queue, but I'm actually using the array. But it's very important because it's very important. This needs to be a queue because we're gonna add like when you're going to append to the end and grab things from the beginning. Like we need functions enqueue and dequeue, and we need them to be very fast. Constant time complexity, but for array, like appending is actually like constant time, but removing first is of n linear time, but we don't have built-in queue in Swift, so I think we should be good just mentioning that in actual implementation we're going to use a queue, but for the simplicity of interview we will simulate it with an array, right? So we have a queue. And as we mentioned in our outline, we need a dictionary, right? So let's go ahead and create a dictionary, var. And again, like we could name it dictionary, but it doesn't make a lot of sense. We can say visited. So like it, yeah, I think this naming better implies like what how this data structure is actually going to be used. And we said the key is going to be an integer and the value is going to be a node. For this problem, it is very important to differentiate like what's the source of truth going to be for you, like where you're going to hold the copies and where you're going to hold the original graph nodes, right? Because for every single node you need to create a copy of it, right? And once you create a connection between two nodes, you want to create a connection between the copy nodes and not between like a copy and original. So we can just go ahead and here say that this whole visitor is going to hold copies, and this queue is going to hold original nodes, right? All right, and then the next step is actually yeah, we need to add queue append. We need to add our node to the queue, and while the queue is empty equal false, we're going to loop, right? And once again, it is very important for BFS and DFS question, but like in general, all the algorithms you're going to need for technical interview, it is very important to have a good structure in your mind for the way you're going to implement it, because there's like a couple things you can like tweak, and like depending on that, your implementation of BFS or DFS is going to be a little bit different. But it is very important for interview not to like mess it up, and don't waste time like trying to guess like which implementation I'm going to use. It's very important to pick one and stick to it, right? All right, so with that being said, let's try to return we need a copy, right? So we're going to take a copy from our source of copies for the node with val, right? This is going to return as an optional, but as an in function declaration we have it optional here, so it's fine, right? So once we are in our loop, the first thing is let's try to take a node from the queue, right? So we're going to say let node equal queue remove first, right? We are using array, right? So we're gonna say for array, this is actually O big of n time complexity, but for Q, it's gonna be big of 1. But like for some problems in Leetcode, it does matter. But for this one, sometimes you can get exceed time constraint exceed or something like that. But for this particular problem, it's not going to cause us problem. So but it is very important to understand, right? So because for array, if we remove the first element, it's actually like what's going to happen under the hood is it's going to copy every single element one index to the left once we do remove the first element, right? So that's why it does need to take all this of n time. But for the queue, it's going to like take dequeue from the beginning and append to the end. It's just like different data structures for different purposes. All right. So once we take this node from our queue, we need to realize this is a node from original graph. So what we want to do is actually, yeah. Let me think. There are a couple of things. Let's see if we not. Yes. Okay. Let's do. Go ahead and here try to put a visited. Like once we add it to the queue, let's say we mark it as visited, or like we create a copy of it and put it in our visited data structure. So we're gonna say visited val equals to, and we the way we're gonna create a copy is use this constructor node dot val, right? So this step is actually very important. I'm gonna say why in a second, but once we get the node, we what we want to do is go ahead and loop through all its neighbors, in node neighbors, neighbors, right? So another thing that is important here is to realize that neighbors actually is an array of optional objects nodes. So we need to unwrap it. So we're gonna use our guard here again. Guard let nay equal nay, else we just need to continue, right? All right. So now we have our nay object, and the next step is actually check if let copy of nay, if we have it in our visited nay val, if we have it in our visited data structure. If we do, it makes it it means that we have already created a copy of it, so we can just access it right here. And what we need to do is add it to our we need to add it as a neighbor to our copy of node, right? So we have created a copy of node right here, and we need to say visited node val, right? Original node value. We access the copy of it through our visited data structure, and we're gonna say it's gonna return us optional, right? So we're gonna say we're gonna use optional chaining and access its neighbors. It's going to give us an array, and we want to append our copy. Once again, a copy of nay right here. Yeah, that should work. And yep. But in else clause, we're gonna what it means is that we don't, for the neighbors we are visiting right now, we don't have a copy of it. So we're gonna go ahead and create a copy. Let's name it copy of nay, and how we're going to do is that we're going to say node nay.val. We're going to go ahead and create a copy of our neighbor, and we're going to do a couple things. We're going to say we're going to add it to our visited nay.val equals copy of nay, right? And we are going to add to our node a copy of nay we just created. And the last thing is we need to add this neighborhood to our queue. And remember how like our queue holds not the original, but not the copy, but the original node. So we're gonna go ahead and say queue append nay, not copy of nay, but the original nay, right? And yep. So that should be it. There are a couple of things that are very important here in this question, and kind of easy to mess up. Like what we could have done here is move this step inside of our loop, and then would end up creating too many copies and like making not the right connection. So it is actually very important to move this back to outside of our loop. Because right here, if we haven't created let's move this back, right? So inside of our loop, like in the first step, we take an object from our queue, make a copy of it, right, and add it to our visited. But as we traverse all its neighbors, we we uh, we would need to, like, if we don't have a copy of it, we will need to make a copy of it and then like add the copy to the neighbors. But once we add it to the queue, like what will happen is we will end up like creating a new copy of a neighbor, like, and rewriting, like we'll create a new node object and yeah, and put it in our visited because the value is going to be the same, but it wouldn't have the right connections, right? So that will mess up the solution. But like one approach would be to create a, I don't know, put an if statement here, but then the code doesn't look very robust and like yes. So that step was very important for this question. So yes, with that being said, let's not forget about the very last step. What you want to do is to, after like you finished coding and you think you have solved the problem, it is very important to take a moment and ask your interviewer if he for you to make a dry run, basically go through your code again and check if you haven't if you missed something, or like you made some typo mistakes, like, or some small logic mistakes, because like it's better to catch those yourself so you don't lose points, and like it again shows your interviewers that you always like double check your work. It's a good sign, and this is something your interviewer is going to pay attention to. So with that being said, let's do a dry run of our code, right? So we created a function we call our BFS. In our BFS, we covered the edge case, and then we created our hold our copies, data structure for copies, and our data structure for original nodes. We add it to the queue, and then um, let's take this this example right here and try to do the dry run with it. So now at this point, it is very actually important to do, like, as you go through your code, to make some notes as comments, so it's easier for your interviewer to follow your line of thoughts, right? So this is empty for right now, but and this is empty for right now. But now, like at this point, we add node. Let's say we add one. We add node one, and then we create for one. We create a copy, and like when we create a copy, it creates an empty array of neighbors, right? So that's going to be it. And then like we check the queue is, if queue is empty, it is not. So we're going to go ahead inside our for loop. We're going to remove the object from the queue. So the queue is going to be empty here. At this step, our neighbor for one is neighbors are 2 and 4. So let's go ahead and say one has two neighbors, 1 and 2. 2 and 4 actually, sorry. So we're gonna check here, unwrap the optional node and check our visited for nay, right? We are right now at nay 1, at nay 2. We can go ahead and say, like, point it this way, just to show that we are at this step right now. And then we check our visited. The visited doesn't contain 2, so we're gonna go here. It's gonna create a copy. Let's move this down here. For visit, it's gonna create a copy of node 2. And when we do create a copy, it's going to create an empty array for neighbors. And then we're going to say that visited, actually visited node, the node is 1, right? So we're going to say access this copy, and I'm going to say that add a copy of nay to the neighbors. So it's going to be like this, and then we append. Let's keep track of our queue right here. Queue. At first it was 1, and then we removed it. So at this step we append 2, and then we we go to the next neighbor, right? And the next neighbor is going to check if a copy of it exists in our visited. So we see that it does not. So I'm going to go ahead and create a copy of 4 with an empty neighbors. Once we do create a copy of it, we're going to add 4 to our neighbor or 1, right? So because node is 1, and we're adding it a copy to its neighbors. right? And then we're going to add also 4 to our queue, right? So now our queue consists of 2 and 4. And once we finish that step, we're going to go back here and check our queue. It's not empty. We're going to remove the first element. So we're going to do the first, and then let's change this to 2. And the neighbors of 2 are 1 and 3, right? So let's change it 1 and 3, and I is going to point to the first one. So we're going to check if I'm going to unwrap and we're going to check in our visited, do we have a copy of neighbor 1? And actually, we see that we do have a copy of it, so we're going to go ahead and access it here. And what we're going to do is going to say that visited node notice to its neighbors, and we want to add a copy of name. So yes, it's just going to add 1 here, right? And then we're done with this step. We'll move to the next neighbors, check 3. Check 3 is not in our visited, so we're going to go ahead and create it and add empty list, right? So at this point, I think it might make sense. You can do like a couple loops. You don't have to go through everything because it depends. You have to check your time. If it's the first question and you are sure you've checked your code, you're sure it works, you can go ahead and say, okay, I think we see that the problem the code does solve the problem and it works correctly. So we can stop at this point. But for example, if it's your second question and your interview doesn't stop you, so maybe it's a signal that you have made a mistake and he wants you to find it, or like you have a small bug and he wants you to find it, and you can keep going, or your interviewer is going to go ahead and say, okay, I think it's fine, and we are out of time, so let's move on to the end of the interview where you can where you get a chance to ask your questions. So with that being said, I think this code does work correctly. We can actually go ahead and copy this code, and let's check. I have it right here. Let's check if we haven't made any mistakes. Let's move it, align it a little bit, and then yeah, we have a call here. So let's run it. See, we have a small typo. Yeah, it's not nay, it's, and other than that, we should be fine. Yep, let's hit submit and check if it does pass all the test cases. Yeah, we see that it does. It's pretty efficient. I think one thing why it's not faster than DFS is because of this remove first. As we mentioned before, it's O of n, so the overall time complexity is going to be a little slow. But okay, thank you for watching. I think we're done here. If you like this video, please hit that like button, subscribe. I'm going to post different videos where we solve Leetcode blind 75 problems. Thank you.